Hello and welcome back to the Quality Excellence channel. I'm Mayank Agarwal, and in today's Lean Six Sigma training, we're going to cover Chapter 20, Non-Normal Probability Distributions. Today, let's talk about data and why it doesn't always fit the neat, familiar bell curve. The bell curve, or normal distribution, is famous for describing things like heights or test scores, where most values cluster around the average. But here's the truth. Most real-world data isn't normal. It's often skewed, lumpy, or has long tails. This is called non-normal data. It's not wrong, just different. Non-normal distributions describe things like wait times, counts, or anything with a natural limit. Recognizing this is the first step to understanding the real world of data. So let's leave the bell curve myth behind and explore the fascinating world of what's not normal. Where does non-normal data show up? It's a question that challenges our assumptions about the world. We often expect things to follow a predictable pattern, a nice, neat bell curve. But what happens when the data defies those expectations? What happens when the data is not normally distributed, everywhere? The reality is, non-normal data is far more common than we might think. It's woven into the fabric of our daily lives, shaping the world around us in ways we often overlook. From the mundane to the extraordinary, non-normal distributions are lurking, waiting to be discovered. Think about waiting on a customer service call, a universal experience that highlights the quirks of non-normal data. Most people wait a short time, a few minutes perhaps, before their call is answered. This is the bulk of the distribution, the area where most of the data points cluster, but a few wait much longer. They are stuck in a seemingly endless loop of automated messages and hold music. These unfortunate souls represent the long tail of the distribution, the outliers that skew the data. That's a skewed distribution. The average wait time might be relatively short, but the experience of those who wait excessively long dramatically alters the shape of the data. Or consider light bulb lifespans, another everyday example of non-normality in action. Most last a while, burning brightly for hundreds or even thousands of hours, providing consistent illumination. Some fail early, succumbing to manufacturing defects or unexpected surges, and a few last much longer, defying expectations and exceeding their rated lifespan. This isn't a bell curve. The distribution is not symmetrical around the average lifespan. It's a Weibull distribution. This type of distribution is commonly used in reliability engineering to model the lifespan of components and systems. Income is another classic example, a stark illustration of how non-normal distributions can reflect societal inequalities. Many people earn average wages, forming the broad base of the income distribution. They represent the working and middle classes, the backbone of the economy. But a few earn extremely high incomes, accumulating vast wealth that dwarfs the earnings of the majority, creating a long right tail. This skewness highlights the significant income disparities that exist in many societies. Even the number of cars passing through an intersection can be non-normal, a seemingly simple scenario that reveals the complexities of real-world data. There's a hard stop at zero. You can't have negative cars passing through an intersection, and the pattern is lumpy, not smooth. Traffic flow is rarely consistent, fluctuating with the time of day of the week, and unexpected events. These examples show that non-normality, far from being an anomaly, is often the rule, not the exception. It's the natural state of things, reflecting the inherent variability and complexity of the world around us. The world's data is rarely symmetrical. Embrace the asymmetry, for it holds valuable insights. So next time you look at data, expect the unexpected. Be prepared to encounter distributions that defy your preconceived notions. Real-world data is wild, untamed, and often unpredictable. And that's what makes it interesting. It's in the deviations from the norm that we discover the most compelling stories. Embracing this helps us understand the world more accurately. By acknowledging and exploring non-normal distributions, we gain a deeper understanding of the forces that shape our reality. Don't force your data into a bell curve. Resist the temptation to impose a preconceived structure on your data. Let it tell its own story. Allow the data to speak for itself, revealing its unique characteristics and patterns. That's the key to real insight. True understanding comes from embracing the complexity and messiness of real-world data. The world is just not that symmetrical. So embrace the wildness, explore the asymmetry, and unlock the hidden stories within your data. So why does it matter if data isn't normal? Many statistical tools like the t-test or ANOVA assume your data follows a bell curve. If you use these tools on non-normal data, your results can be way off. Imagine a drug trial. If recovery times are skewed, but you assume normality, you might miss a life-saving effect or make a bad call. That's not just a math error, it can have real consequences. Good data analysis means checking your data's shape before running tests. Don't just trust the default settings, examine your data first. Always ask, is my data normal? That's how you avoid costly mistakes. We often assume data follows a normal distribution, but what happens when it doesn't? What if the data tells a different story, one that deviates from the familiar bell curve? If data isn't always normal, what is it? What other shapes and patterns can data take? And what do these patterns reveal about the underlying processes? Let's meet some key players. We're about to embark on a journey through the world of probability distributions, each with its own unique characteristics and applications. The exponential distribution models time until an event. It's all about predicting how long something will last or when something will happen, like waiting for a text message, or the time until a machine breaks down, or the duration of a phone call. Most events happen early, meaning the probability of an event occurring decreases over time, with a long tail. This tail represents the possibility, albeit small, of very long durations or waiting times. The Weibull distribution is used in engineering, providing a flexible way to model various failure patterns. To model failure times, helping engineers understand and predict when equipment might break down, whether things break early, showing infant mortality, or wear out over time. It helps determine the lifespan and reliability of products. The log-normal distribution describes things like income, where a few individuals earn significantly more than the majority, or city sizes, where a few megacities dwarf the numerous smaller towns. Values can't be negative, because you can't have negative income or a city with negative size, and a few are extremely large. This creates a skewed distribution with a long tail on the right. If you take the logarithm of log-normal data, applying a mathematical transformation, it becomes normal. This property makes it easier to analyze and model. The binomial distribution handles counts, specifically the number of successes in a fixed number of trials, like how many heads in 10 coin flips, where each flip is an independent trial, or how many products are defective in a batch. It's a fundamental tool in quality control and risk assessment. Each distribution tells a different story, offering insights into the underlying processes that generate the data about the world. They help us understand patterns and make predictions. Knowing which one fits your data, which distribution best describes the data you're working with, is crucial. It allows for more accurate analysis and informed decision-making. These aren't just math curiosities confined to textbooks and academic exercises. They're tools for real-world problems. They have practical applications across various fields. The right distribution, when applied correctly, gives you better answers. It leads to more reliable predictions and effective solutions. So get to know these shapes, familiarize yourself with their properties and applications. They're your new best friends in data. They'll help you unlock insights and make sense of complex information. The world is more than just a bell curve. Embrace the diversity of distributions and expand your understanding of data. Meet the Poisson distribution. It counts events over time or space, like calls per hour at a call center. If the average rate is low, the data piles up near zero. As the rate increases, it starts to look more like a bell curve. Use binomial for a fixed number of trials, Poisson for random events over time or space. These distributions, exponential, Weibull, log-normal, binomial, and Poisson, are your essential non-normal tools. Each is a specialized tool for a specific job. Using the right one makes all the difference. How do you spot non-normal data? It's a crucial skill for any data analyst or scientist. Understanding the distribution of your data is paramount before you even begin to apply statistical tests or build models. Become a data detective. Your mission: to uncover the secrets hidden within your datasets. Look for clues that suggest your data might not be behaving as expected. Start with a histogram, a bar chart showing how your data is spread. It's a simple yet powerful tool for visualizing the shape of your data. Is it symmetrical, like a bell curve, indicating a normal distribution? A symmetrical histogram suggests that the data is evenly distributed around the mean, or does it have a long tail, stretching out to one side? This is a sign of skewness, indicating that the data is not evenly distributed. Next, use a box plot. This provides a visual summary of the data's distribution, highlighting the median, quartiles, and outliers. If the median isn't centered within the box, or the whiskers are uneven in length, it suggests asymmetry. Your data is probably skewed, meaning it's not normally distributed. Skewness can significantly impact the validity of certain statistical tests. Try a normal probability plot, also known as a QQ plot. This plot compares the quantiles of your data to the quantiles of a normal distribution. If your data forms a straight line, closely following the diagonal, it's likely normal. If it curves significantly away from the line, it's not. Deviations from the straight line indicate departures from normality. Visual tools give you quick clues, allowing you to quickly assess the distribution of your data. For a formal check, to confirm your visual assessment, use statistical tests designed to test for normality, like Anderson-Darling, a powerful test that is sensitive to deviations in the tails of the distribution. Or Shapiro-Wilk, another widely used test, particularly effective for smaller sample sizes. A small p-value, typically less than 0.05, means your data is likely non-normal, leading you to reject the null hypothesis of normality. Combine visuals and tests for a complete picture, providing a robust assessment of your data's distribution. Don't just guess, let the data show you its true shape. Rely on both visual and statistical evidence to guide your conclusions. Spotting non-normality is the first step to good analysis, ensuring you choose appropriate statistical methods. The right diagnosis leads to the right solution, preventing you from drawing incorrect conclusions from your data. Always check before you test. Verifying the assumptions of your statistical tests is crucial for ensuring the validity of your results. That's how you avoid surprises and build confidence in your data-driven decisions. By carefully examining your data's distribution, you can ensure that your analysis is sound and your conclusions are reliable. Found non-normal data? No problem. Use non-parametric tests like the Mann-Whitney U-test, which don't assume a bell curve, or try a data transformation, like taking the log of each value, to make the data more symmetrical. Sometimes, fit a different distribution, like Weibull or exponential, to match your data's true shape. For large samples, the central limit theorem says averages will look normal, even if the raw data isn't. Choose the right approach for your data and your question. Don't force normality. Work with what you have. The right method leads to better answers. That's how you turn messy data into real insight. Embrace the variety. Let's see this in action. At St. Jude's Hospital, administrators wanted to fix long ER wait times. They collected data, expecting a bell curve, but the histogram showed most waits were short, with a long tail of a few very long waits. The average was misleading. Most patients waited less than the average. Dr. Sharma, the analyst, ran a Shapiro-Wilk test, confirming the data was non-normal. The shape looked log-normal, so she applied a log transformation. The new histogram was symmetrical now. She could use standard tests. By identifying and correcting for non-normality, Dr. Sharma gave the hospital accurate insights. The result? Better decisions and real improvements for patients. This is why understanding your data's shape matters. Don't assume. Investigate. The right approach leads to real-world impact. That's the power of good data science. We've busted the bell curve myth and explored the wild world of non-normal data. Here's your checklist. First, always visualize your data. Histograms and box plots are your best friends. Second, confirm with a formal test like Shapiro-Wilk. Third, choose the right solution. Non-parametric tests, transformations, or fitting a new distribution. Don't force your data into a bell curve. Let it speak for itself. By following these steps, you become a true data scientist. Listen to your data's story. That's what science is all about.